In this video, we're going to take a look at the BoxCox transformation applied to a couple of different data sets. First thing I'm going to do is require the mass package. Okay, and then I'm going to take a look at the savings data package from Faraway. We've already seen this package before, and just to review here what this is about, this gives an average over a 10-year period from 1960 to 1970. The savings rates, that's what SR is, savings rates for personal savings rates divided by, or personal savings divided by disposable income. POP 15 is the percentage of the population under age 15. POP 75 is the percentage of the population over age 75. DPI is the per capita disposable income in dollars, and DDPI is the percent growth rate of DPI. Okay, so what we want to do is check out and see if the BoxCox transformation seems like a good idea for this. Okay, so what I'm going to do first is I'm just going to make a couple of plots here, and I want to put them side by side, so I'm going to use that par mf row command, and I'm going to partition that graph window so that it has one row and two columns so that I can put my graphs side by side, one to the left and one to the right. And then I'm going to run BoxCox on, I guess I want to do the, I need to get a linear model for my savings model, SR versus POP 15, POP 75, DPI, and DDPI. And I want to do BoxCox on that linear model, and I'm going to use this option called plot it. Okay, I'm going to say plot it equals true. When it does that, it's not only going to store all that the lambdas and the log likelihood function values and stuff like that. It'll also make a plot, and we'll see what that does. In fact, you can see that now over in your graph window, it has in fact made a plot. All right, so this plot is of the log likelihood function versus lambda. So you can see clearly now that in fact as lambda increases, the log likelihood function increases until you get to a certain point, and then the log likelihood function begins to decrease. So this is seems to be a monotone function, and it looks like a 95% confidence interval then for the actual lambda that maximizes this log likelihood function is somewhere between maybe 0.6 and 1.3 or something like that. It straddles 1 at any rate. We can actually zoom in on that a little bit if I just change the range for the lambdas there. Okay. Now you can see it a lot better. You can see that probably our best guess for lambdas is about 0.95, 0.96, something like that, something really close to 1. Because this confidence interval straddles 1, there seems to be insufficient evidence to conclude that the true lambda value that would maximize the likelihood function for this kind of transformation is anything but 1. Okay, so let me ask you this then. What happens if you take 1 for lambda? What happens if you stick that back into the transformation function for BoxCox? Remember that transformation function is y to the lambda minus 1 over lambda if lambda is not equal to 0. So if I take y to the 1 minus 1 over 1, what's that? That's just y to the 1 minus 1, which is y minus 1. Okay, so if I transform my response, which is y, to just y minus 1, all I'm doing is shifting it down. I'm shifting this response function down 1, and that's not much of a transformation at all. In fact, I could just easily flip that negative 1 to the other side of the equation in our model and let it be rolled into our beta naught coefficient. Okay, so if lambda turns out to be something really close to 1, if the confidence interval straddles 1, then probably you don't need a BoxCox transformation. Okay, so let's take a look at another model though. In your book, Fairway goes on to look at the Gala, or Gala, I guess it would be, package. So let's take a look at that one. And just to remind you, the Gala package is on the Galapagos Islands. There are 30 Galapagos Islands, and these variables are species, which is the number of plant species found on the island. Right, you have all these different islands here, and these are the numbers of plant species. Endemics is the number of endemic species. Area is the area of the island in squared kilometers, and elevation is the highest elevation of the island. Nearest is the distance from the nearest island in kilometers, and Screws is the distance from Santa Cruz Island in kilometers, and adjacent is the area of the adjacent island in square kilometers. Okay, so let's get build just a plain Jane simple linear model for species versus area and elevation, nearest and screws and adjacent. Okay, and I'm going to do like I did before. I'm going to get a new window there and partition it so that I can make two graphs side by side. I'm going to do BoxCox transformation with use the plot it option, set that equal to true. My lambda values are going to go from -1/4 to 3/4 by 5%. I'm doing that because Fairway does that. Okay, no, really, if you didn't know that, I mean, if you didn't know what a good range is for lambda, then just leave it out and then take a look at the graph, and then after you look at the graph, you can tell how you can zoom in. Okay, so you can see that in fact it does go from about -1/4 up to 3/4, and so here's our log likelihood function. Looks like it's maximized somewhere around lambda equals 0.3 or something like that. Here's 0.4, here's 0.2, so maybe it's around a third. Okay, clearly this 95% confidence interval does not straddle 1, so it could be that BoxCox is actually useful in this case for transforming the data. Maybe it alleviates some kind of a problem. So here's what I'm going to do, like we did in a previous chapter. I'm going to recall that my this BC trans stuff is actually some numeric arrays. Okay, and there's an X array and a Y array there, and oops, I got the wrong thing there. I'm going to call my X stuff, I'm going to set that equal to lambda, and the Y stuff equal to the log likelihood function material there. And BoxCox, I'm going to set equal to, I'm going to bind lambda with column bind the lambda values with the log likelihood function values. This BoxCox variable here is just that. It's just a variable. Remember, don't confuse this with the function. I probably should have called it something else. But okay. Now what I'm going to do is I'm going to get I'm going to take that BoxCox double array and reorganize it so that it's in order of decreasing log likelihood function values. And the idea is you want to pick the lambda value that maximizes that log likelihood, right? So there they all are. Let's just scroll up to the top. This is the lambda value you want right here, this 0.31565656. This is the lambda you want because it maximizes the log likelihood function at this point. This number here, this -44, 60, whatever, is closer to 0 than any of these others, right? So another way to get at that, in fact, I'm going to store this in L for lambda, L for lambda, is I'm going to store this. It's the element from the first row, first column, and I'm going to put that into L. And if you type L, there it is. That's my lambda value. That's my best guess for the for lambda. Yeah. So then what you want to do is you want to use that lambda, and you want to transform that response variable accordingly. And so you can see what I've done there is I'm going to build a linear model of species raised to the L. That's careful there. That's not a 1. That's an L. Species raised to the L versus area, elevation, nearest, screws, adjacent, etc. Okay. And if I do that, then and if I do summary of summary there, okay, get your usual output. Again, just be careful and realize that you are actually you're modeling species raised to the 0.31565 as this linear combination of these variables. Okay, so if you want to recover your species variable there, then you have to raise both sides of your linear model to the 1 over this power. Okay, so that species is modeled as all of this stuff, area plus elevation plus blah blah blah, all of that raised to the 1 over this power. Okay.